in this video, we will be continuing our discussion on variables. We're going to be expanding into the realm of conversion. Conversion? Yeah, you need to know how from time to time to take one data type and convert it to fit into another data type. Check it out. Notice how I drew those different sizes? What if you had a variable that was of type float? Boy, that holds all sorts of information, and you needed to put that information over into an integer variable because you had a particular routine that did work on an integer. Well, you would need to know how to convert the data that was in the float variable over to a variable that was of type integer. And there are several ways that we can go about doing this. But this is obviously very important, and it's very common as well. If you happen to make it through Canon 1 and 2 back in the Volume 1 series, you will recall that Logan had to cast the square root method that we used in the distance method. Okay, had to cast it from a double to a float because our routine worked with floats, but the math routine, square root, gave us a double back, right, Logan?
Right. The math routine was going for the full precision of a double, but in our case, all we needed was a float.
That's right.
So we cast it over to a float so we could use that value.
That's right. So knowing how to cast data types from one type to another is extremely important. You're going to be doing it all of the time. We're going to start doing it all of the time in the games that we're going to be creating. So we need to go ahead and take a video and focus on it. Now let me give you a quick warning. There is a lot to this video that we're going to be going over. There's a couple of tables that I'm going to be writing out, and it is not necessary that you watch as I do it. That is why you have that track bar down there on your video player. That's right. Feel free to grab that thing and simply move it forward in time to skip past me drawing all this stuff out. Why am I drawing it all out? Simple. I want to give you guys a reference that's embedded in this video that you can come back to and look at it any time. So to me, it's very important that I give you this information. I look at it like this. The more information that I put in these videos doesn't hurt anyone because they always have the fast forward button. So with that out of the way, let's go ahead and see how we can do type conversions. All right. So let me go ahead and clear this off. Now, in casting from one data type over to another, there's two ways that we can go about doing it. We can do an implicit cast or we can do an explicit cast. So let's go ahead and jot this down and give a really quick overview. Implicit, explicit. Implicit's real simple. Basically, the compiler says, hey, the information that you're wanting to store from one variable over into another variable will safely fit without the risk of losing any data or any precision. So let's just do it. That means you, as the programmer, do not have to do anything special to intervene to make that conversion happen. What am I talking about? Well, let me give you a really simple example. I'm going to make up my own data types real quick, and here's why I'm doing this. Remember back when we did the predefined data types video and I drew out all of the different bits? I drew out a byte and that had 8 different bits in it. Well, obviously I'm not going to want to draw out all of the memory locations, or excuse me, all of the bits required to hold a float and all the bits required to hold an integer and then show you. I mean, that's just going to be huge. I don't have enough room right here and I'd be drawing boxes forever. So we're going to say we have one data type that has 3 bits in it. And then we're going to have another data type, let's say, that has 1, 2, 3, 4, 5 bits in it. Now, let's just pretend we're going to stipulate, everybody say that with me, we shall stipulate that this is an integer and that this is a long. Now, we're all stipulating. That means you too, Logan. So we're just going to, at this point, pretend that an integer is only 3 bits and that a long happens to be 5 bits. The bottom line is we see that the integer is smaller than the long, right?
Right. And you do indeed, you'll have the same type of information, but you'll just have more of it in the case of the long.
That's right. So what I want to do, let's go ahead and create a really fast example here. Let's just say that I had integer x and that I had long z, and I wanted to say z equals x. This means I'm wanting to take an integer and put it over into a long. Now let's pretend that I am storing a 5 represented through binary here, in the bits for the integer. So we are holding a 101. If you have no clue what I'm talking about, go back and watch that predefined data types video again, and you'll see where I discussed how we come about figuring out binary numbers. Okay, so if I want to put this over here into the long, what's it going to look like? Well, that bit goes there, that bit goes there, that bit goes there. And then we can simply populate the rest of the bits with 0. We know that this number right here is a 5. And you know what? This number right here, it is also a 5. Now, granted, we have 2 new bits, but those high bits did not have to be set. There's no reason for them to be set because the integer did not have those high bits to begin with, so why should we set them to anything other than 0? Right, Logan?
Right, and the key there is that you were able to represent the value 5 in the long data type because there is enough information in the long to represent 5. There's more than enough, but you don't necessarily have to use it. You can, in fact, represent 5 in both your long and in the int.
Exactly. So in this particular case right here, the compiler knows that we can safely put an integer into a long variable without the risk of any of the data becoming messed up, without the risk of losing data or precision. So it will implicitly do it for us. So this is implicit. Let me fix my eyes. So there we go. All looks good. Now, let's take a look real quick at an example where an explicit cast is required. What if we simply flipped our example above and we had this? So here's our int, and then here comes our long. A long box. And it held 1, 2, 3, 4, 5. And let's say that it had a 1, 0, 0, 1, 1 in it. And we wanted to take this long and put this over into our integer. Ooh. So now, if this is x and this is z, same as we had above, and we did something like x equals z, the compiler would immediately realize that we were trying to take a larger data type and fit it into the smaller data type. It would say, we run the risk of losing information. And why do I say we run the risk of losing information? Check this out. If this happened to have been a 0 right here, and it was 0, 0, 0, 1, 1. This could have translated nicely on over here because it would have been like this, 0, 1, 1. We didn't lose any data, did we, Logan?
No, we're still representing the exact same number.
But at the same time, if this over here would have been that original number that I had wrote in there, now we would lose data.
Right, we'd have, after we did the conversion, we'd have 2 different values.
That's right, and that is definitely a problem. So the compiler is not going to let this go. You have to go in there and explicitly tell the compiler, I need to convert Z over to X. I need to convert the data type that's being stored in Z. So it's going to look a little different. You're going to see something that looks like this. We will use a cast operator, and we're going to say we're going to be casting to type integer Z. All right? This tells the compiler, look, we know that we've got this data type that happens to be big, but we've got faith that taking what's in it and putting it over here into this smaller data area isn't going to be a problem. Just have faith in us. What the compiler does is it puts full responsibility onto you, the programmer, to handle how this is going to take place. Meaning that if you have a problem, if there's data loss or precision loss, that's your problem, okay? Not the compiler. So by doing this, the compiler will say, all right, that's cool, and we'll simply do it. So in this case, this was us going there and explicitly telling the compiler. So this is an explicit. Did it again. That's an explicit cast, okay? So now that we've seen a very quick overview, let's break it down. Let's start off with implicit casting, and what I want to do is give a couple examples. I'm going to have Logan jump over into Visual Studio and code these examples so that you can see it in action, and then what I want to do is give you a table of all of the different types that we can safely convert to other types. Now, let's go ahead and wipe all this out and start writing. So our implicit And let's not do that. Let's try writing a little bit lower. So our implicit example. Let's do something along the lines of, we're going to create an int Logan, and we'll call it x, and we'll put the value 10 in it. Simple enough. We'll then come in here and we'll create another integer. We'll do y, and we'll put a 35 in it. Now I want to create a long, and it will be z. And what I want to put in here, let's do this. Let's have a little bit more fun. We'll take that out, and we'll drop down to the next line. We'll keep everything as clear as possible. Now we're going to take z and initialize it with x plus y. Ooh, we're getting fancy now. So I'm taking two integers and adding them together. So after this expression evaluates, we still have an int. Okay, that's the result. It's still an integer. And this integer needs to be put over into a long. Not a problem, because the long has plenty of space for everybody from the int. In fact, it's got space left over. So this is an implicit conversion. As you can see, we did not have to do anything special whatsoever. We just simply said, hey, z equals x plus y. So Logan, if you could real quick, let's jump over and code this and demonstrate that the compiler doesn't care. No warnings, no nothing.
All right. So I'll bring up Visual Studio and let's start a console project. So I'll bring up our project. And now we need to define some variables, some integers. We had an int x that was set to 10. We had an int y that was set to 35. And we had a long z. Alright, so we wanted to initialize z to the value of x plus y.
Which should be 45. So let's go ahead and console, write it out, and then do a read line.
Alright, we'll grab our console, we'll write this out. Let's write out z, and then turn around and do a console read line. And there we go.
Alright, so looking at this real quick, we are definitely dealing with an integer that needs to be put into a long. So we're definitely dealing with two different data types here. So let's make sure this works without the compiler complaining at all. So let's go ahead and hit F6 just to compile it. Look at that. No warnings whatsoever from the compiler. Let's run it. We should even see 45. Aha! Printed out on the console. Fantastic. So no problem whatsoever with that. That was an implicit conversion. So if we were jump back over here, another real quick example. So let's just come up here, draw a line, and let's see another type we could pick on. How about, here's something interesting. Let's do a char. So a char, and let's call this something like cvar for C variable equals, and let's put an A in it. And what is an A? A is like 96 or 97?
I think it's 97.
97, okay. So that's going to be the value. Now remember, our char is 16 bits, okay? Now let's go ahead and turn around and create an integer. And let's call it, I don't know, ivar. I'm going to be creative with names tonight. And let's put, actually just because we're tight on space, let's move down to the next line. And let's just go ahead and say ivar equals cvar. So now we're saying take something that has 16 bits of information and put it over here in something that has 32 bits of information. Can we fit? Heck yeah, we can fit. And tons of room left over. Double the amount of room. I mean, we got a whole nother 16 free bits are just going to be set to 0. So we should see ivar containing a 97 when we're done, because the 97 is the representation for A, okay? Or A is the representation for 97, depending on how you want to look at it. So Logan, let's code this up real quick.
All right. Let's jump back over into Visual Studio, and I'm just going to clear out the implicit example, or
okay.
this implicit example.
Sure.
Let's make the ivar and cvar variables. You began with the char, where you had cvar, and you had set that to A. And then you had the int ivar, and then we initialized ivar to be whatever cvar was.
Exactly. And now let's go ahead and write that out.
So we'll change our right line to write out ivar, and we can compile.
Ooh,
Indeed, we can.
No errors. And let's make sure 97 is what we get on the console. Haha, 97. Not a problem. Fantastic. That is exactly what I was looking for. So let's go ahead and jump out of here. And we'll come back over to our whiteboard. So there are some examples of explicit casting. What does it mean? It simply means that we, the programmer, do not have to do anything special whatsoever. The compiler will take care of casting the type from one type to another. Okay? Now what I'd like to do, and this is going to be a little bit boring, and you are welcome to fast forward now, is I'd like to draw out a table that shows all of the different types and what the types can safely be converted to. And I'm just doing this for you guys so that you have it as a reference. So let's go ahead and get that out. And let's see, I'm going to define a real quick table here. So something like this. Something like this. And this will give me enough room to do type. And then with any luck, this should give me enough room to finish it all off. So over here, what I'm going to do is show the type we want to convert. And this is what we can safely convert to. Meaning this is what we can use implicit conversions. Alright, so let's go ahead and come over here. Just trying to make this look kind of nice. And we shall begin. Start out with a byte. Small little guy. That means he's going to fit into, well, just about every number type that we have out there, right, Logan?
Everything else is generally 8 bits or higher, so as a matter of fact, the rest of those in the list seem to be 16 bits or higher. So yeah, there would be absolutely no problem in storing that in a wide variety of other data types.
So we start out with, we can easily cast this, safely cast this, which means there's no risk of data loss or precision loss. So we can cast this over to a short. We can cast it over to an unsigned short, to an int, to an unsigned int, to a long, to an unsigned long. Notice how the numbers, the types just keep getting bigger and bigger. To a float, to a double, and to a decimal. Alright, let's go ahead and draw a line here. So what does this read? Or it's basically just saying that if we have a byte, we can implicitly convert it over with no problem to a short, blah, 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 blah. Everything that you see on that line right there. There's no extra requirements from us, the programmer, because the byte will safely fit into all of those data types. All right, so next one we're going to take a look at is going to be the signed byte. Okay, push my T and Y a little closer together. There we go. And the signed byte will go into a short. It's going to go into an int. And you'll notice that losing unsigned, think about it. This is a signed byte. So just kind of think back to when we talked about all the predefined types and we went over the sizes and the ranges that they held, okay? Because we've got to be able to take each of these types and safely convert them over without the risk of losing anything, all right? Now, int, I'm sure with that you can easily see what I'm talking about. So next is a long. Next is going to be a float. Next we can convert to double. And we can also safely convert over to decimal. All right, very nice. Next type I'd want to look at is going to be the short. And with the short, we can convert over to an int, to a long, to a float, to a double, and to a decimal. All right, moving right along, making progress. Next one in the list is going to be an unsigned short. Which can safely convert to an int, an unsigned int, a long, which means an unsigned long, a float, a double, and a decimal. All right, moving right along. Next one is going to be the integer, the int that we all know and love. And the int can convert over to a long, a float, a double, and finally a decimal. All right, let's go ahead and run our line on over. All right, so the next one is going to be an unsigned int. See, hopefully by now you have fast forwarded because you can see how boring this is. All right, and this is going to convert over to a long. Of course, now we're going to be adding in all of our unsigned types that are large, and we'll hold this as well, such as the unsigned long, float, the double, and finally the decimal. How are we doing over there, Logan?
I'm doing good, and just noting the fact that as you start dealing with larger and larger data types, that of course diminishes the other types that you can implicitly convert to, because obviously you're running out of things that that data type will fit into.
Absolutely. Our int right here cannot fit, so this is going to be a big no. That's a no. It cannot fit into that short. So, yeah, you don't see the short listed over here in all the types that we can safely convert to. All right, so moving right along.
See, now there's value to watching the whole video, because if you didn't, you wouldn't know that that wouldn't...
Why did he draw the line?
How do you store an int in a short? I don't understand.
Okay, so that nobody's confused. There we go. All right, so the next thing we're going to do is throw in there. We'll keep our table nice and clean. We're going to have a long. And with our long, not ling, we can convert it to a float. But Logan's absolutely right. Our table is going to get smaller and smaller now. And my hand is happy. A double and a decimal. All right, so now, keep it nice and neat looking. The next one that we're going to have is going to be an unsigned long. And with the unsigned long, we can basically convert this over to a float, a double, and a decimal. Okay, almost there. So the next one is going to be a float. And with the float, we can convert it to, ready for this, a double. That is it. Notice how decimal has dropped out. That's because we're now dealing with floating point numbers, and we're dealing with a decimal point. So things change just a bit from the decimal type to our floating point types. So with this, a float can only go over to a double. Who does that mean a double can go over to? Nobody. So we're not going to find double in the list. So the next thing that we're going to find is going to be a char. And now, who can the char fit into? Wow, here comes the party. So it can go into a U short. So an unsigned short, an int, an unsigned int, a long, an unsigned long, float, a double, and a decimal. All right. So now I can come in here and just clean this up a little bit. And now, if you ever fast forward through your video, you can quickly find a table that demonstrates all of our numeric types that we can safely convert to using implicit casting. Okay? You'll notice that bool is not on there and string's not on there either. We can't just implicitly cast those to some other type. String is, well, holding all this textual information, and a bool is holding only a true or a false. So it is something completely different, though we will be talking about string in a couple of different ways in a few minutes. All right, so this is once again implicit. Looking down here at my notes, that's everything I wanted to talk about. Whew. So let me go ahead and bring up this guy and add myself another sheet. And we'll simply hide this. And on this sheet, what shall we talk about now? We're going to talk about explicit casting. So let's go ahead and come up here. IT, that's right. Explicit example, that's what I want to write. All right, explicit example. Remember, the key thing here is we are telling the compiler that, hey, we want to convert this data from the data type it currently is to a specific data type that is defined within the cast operator that we're going to use. And the compiler says, okay, and just lets us do it. And that makes us responsible for this conversion, if we're going to lose data or not. We'll talk about that in just a second. So let's go ahead and do an example real quick. So how about we throw some floats in. So float A is going to be equal to, about we do 12.65 float. And how about we do another float, we'll do a similar example. B equals 16.22. Terminator. And now let's create a good old int. Call it C. And now, Logan, I actually want to cause a problem here. I'm going to say C equals A plus B. Now, this is us trying to use an implicit cast. We're trying to have the compiler take A and B, add them together. The result, of course, put over into an integer, and it's not going to fit. That's going to be a problem. We're trying to say, look, add these guys, these two floats, put it into an integer. The compiler is going to stop us right there. So, Logan, before I write anything else here, let's go ahead and code this example out real quick.
Okay. I'm going to drop down and bring Visual Studio back, and I'm going to wipe out the code for the char to int example.
Sounds good.
So we'll just jump in right above that. Now, we need to make some floats, so we'll have a float A, and we'll set that to 12.65 F. And a float B initialized to 16.22 F. Now we want to declare I, so I have an integer, C.
Yeah.
I have an integer called C.
Mm-hmm.
And then on the next line we're going to attempt to store A plus B into C. And we'll see what happens.
And let's go down to the right line and tell it to go and write out C.
Okay.
Even though we're not getting there. Okay, so let's go ahead and compile and see that we get an error. Check this out. Cannot implicitly convert data type float to int. An explicit conversion exists. Are you missing perhaps a cast? I love it. It is so awesome with its errors because it's dead on. I love how it just kind of asks you that question. You have screwed up. Is this perhaps how? So let's go ahead and jump back in here and let's add that because this messed up just like we said it would. We can't implicitly convert. We need to explicitly do it. So this is where we're going to use a cast operator. So a cast operator is real simple. Opening parentheses, what data type is our target? So it's going to be an int. That is what we're targeting. And then I'm going to go ahead and open this up, open another parentheses, and put A plus B in there. I'm doing this just to make sure that A plus B is handled just so that I don't have A trying to be converted to an int.
Right, we try to add the int A to the float B, which might end up with a float again, and then we're back to our original problem.
Exactly. So in this case, having the parentheses around A plus B will cause A plus B to evaluate, and then we will simply convert it, we'll cast it over into an integer. So this right here is nice and legal as long as it has a terminator on the end. Again, just for those of you that are following along and taking notes, this is a cast operator. All right, Logan, so let's go ahead and fix our code back over in Visual Studio.
Okay. I'll begin by putting the A plus B operation in parentheses so that I can drop in before that, do an opening parenthesis, write in the type, which is int, then a closing parenthesis, and then we fixed our line.
There we go. Now, taking a look, go ahead and just hit F6. So we're not running it yet, but he did compile, and look, no errors whatsoever. So now the compiler is happy. Taking a look at this, 65, 22, 6, 7, 8. Okay, so that's going to all just simply be truncated. So 6, 7, 8. So the answer is going to be 28. That is what will end up in C because we cannot have decimal points in C. So let's go ahead and run it and see that we have 28 dink written out to the console. So there you go. Very nice. That's what we were looking for. Now remember, go ahead and close that, Logan, thank you. Now remember, doing this right here by explicitly converting or casting, we are telling the compiler we will assume all responsibility for the conversion. So what ends up happening if we end up with a number too big being stuffed into too small of an area? So let me go ahead and jump back over here and let me give you another example and let's see if we can have a little bit of fun with it. So come back over to our whiteboard real quick and let's see. Let's just go ahead and wipe the board real quick. So here we go. We're going to do an int and we'll call this int AA. And we will put 126 in AA. Now what I'm going to do is create an int called BB. And in BB, I'm going to put 127. Now I'm going to create a byte. Okay? And I'm going to call this byte CC. Now what I want to do is say CC is going to be equal to AA plus BB, but I need to cast it over explicitly, so I know that I need to, because the integer is too big to fit into a byte, so the compiler would stop me if I tried to implicitly do it. So I'm going to come in here and say, let's cast over to a byte the result of AA plus BB. Now, before we actually type this code in here, let's all think back to that predefined data types video that we did where we showed you all of the ranges for our different types. When we talked about the byte, let me just come over here and draw a quick line. What was the byte? It was an 8-bit unsigned integer, right? It allowed a range of 0 to 255. Okay, that was the range that we were allowed to use. Now, right now, if I was to add these two numbers together, what result am I going to get? We're going to get 253. Well, 253 fits in that range without any problem. Agreed, Logan?
Agreed.
Meaning that we're not going to have anything bad happen here whatsoever. Let's go ahead and code this out and add a write line as well, writing out what we have in C after that, or CC, after that last line executes.
Okay. So once again, jumping back to Visual Studio, I'm going to wipe the last example, and we'll begin with some ints. We'll have an int AA, which is initialized to 126. We'll have an int BB, which is initialized to a value of 127. Then we'll have a byte called CC, which is not yet initialized. Then we'll drop down and we'll initialize CC to be equal to the casted version. So we'll cast some data to a byte, and that data is going to be the expression AA plus BB. And terminate that.
And then let's go ahead and simply write out CC. Okay, so doing this, once again, we should see 253 because 7 and 6 is 13. So there's your 3. Carry the 1. 2, 2 is 4. 1 is 5. And then 2. So 253. Let's go ahead and execute. All right, 253. Fantastic. It is working exactly like we say. Let's close this. Now let's do this. Let's have some fun here. If you change the 126 to 127, now we're going to have 254. Let's confirm. All right, 254. Now pick one of those and change it to an 8. And run it. We, ladies and gentlemen, are at the limit of what a byte can hold. What happens if we add one more number into one of our integers and try adding the two numbers together so that we get 256 as the result of the two added integers? Let's go ahead and close this and change that 7 down below to an 8 also. This gives us 256. What happens? We get 0. All right, don't panic. First of all, you'll notice that the compiler didn't freak out and go, whoa, we've got a problem. No, of course it's not going to do that. Why? What did I tell you? When we use explicit casting, you assume all the responsibilities of what takes place with the data when you go from one type to another. If it screws up, you lose precision or you lose data. Compiler doesn't care. It's, it fills the bits with whatever it can fill the bits with. So let's go ahead and close this. Now, just in case you're thinking that, oh, we're always going to be stuck at 0 if there's a problem, watch this. Take one of those, Logan, and make it 129 and run it. 1. Now, all right, close it. Now, make the other one 129. Run it again. 2. Oh, we've wrapped around. How cool. The problem that we've created is known as an overflow. So we have an overflow right now. If we weren't paying attention with our code, we could get ourselves stuck in a situation where by casting data, the data ended up being too big. We had an overflow. It wrapped back around. The compiler didn't throw up, and your continuing routines may use that data. The data is going to look good. That's not a special 0 or a special 1 that you just saw. It is the value 0. It is the value 1. So your routine will now work with that data, but guess what? It's going to be wrong, isn't it, Logan?
Right, and it can produce some very unexpected results. For example, if you were adding on to a number, and you were therefore expecting that number to be bigger than it just was, but instead you overflowed it and it wrapped back around, now you'd be dealing with a smaller number.
Right. So just keep that in mind. So the next thing you might be thinking, at least the first thing I thought when I had learned this was, oh, wow, man. Well, is there any way in code that I can check to see if I'm about to have this problem because of this cast that I'm doing, this explicit cast? And the answer is yes. So what I'm going to do is come back over here to the whiteboard real quick and give you a very fast demonstration of how we can do this. We have two keywords that we can use. We've got a checked and an unchecked, okay? Two different functions that we can use. So how do we use checked and unchecked? I'll check this out. I'm actually extending this line now. All we've got to do is come in here and say check, parentheses, parentheses. So I have put the entire cast inside of checked. The result of this is going to go back over into CC. Now, if there's, and this is at runtime that checked is called, okay? If checked receives an overflow, what it does is it is going to throw an overflow exception. That means that, yes, it's going to look like the program just kind of crashed right back to Visual Studio, and we're going to have to stop it ourselves, and it's going to highlight where it crashed out at, and it's going to say that there is an overflow exception. Now, we can go in there and we can do try and catch and basically catch this thrown exception and deal with it. That's outside of the scope of this video, but I want to show you that we can have the code monitor for and throw an exception if we do indeed cause an overflow. It's very important to know this. So Logan, let's go ahead and throw checked in there real quick just to show them how this works.
Okay. So back to Visual Studio for a moment, and let's put checked in around this cast. So we'll say checked, and then place the cast in parentheses.
Okay. So now that we have used the keyword check, let's go ahead and, all right, first of all, let's go ahead and take the 129 and let's go ahead and turn it back to 126 and 127.
All right.
All right, so we know that this was good. Let's run it. Check it out. Everything runs beautiful. We have a 253. That's outstanding. All right, let's close it. Now give me 8 and 8. All right, so we know this is going to be a problem. Watch. Runs. Hard drive spins for a second. Boom. Puts us right there. Now here's the most important part. Check this out. An overflow exception was unhandled. This is fantastic. This now gives us something that we can use. We can basically try this. If there's a problem, we can catch and handle this exception. And again, we're going to get into all that stuff later on. But right now, I just want you to feel comfortable that we can handle this. So it's not necessarily a problem. All right, now, Logan, let's go ahead and stop it. And now let's go ahead and take a look at one other way that we can use check real quick. We can also use it like this. 1 second, please. We can basically use it on an entire block, which is pretty cool. So if I come back in here and say CC equals, so that's what we had before with the terminator, I can come up here and I can say checked. And now, instead of using an open parentheses like a function call, I can go ahead and use an open curly brace. And Logan, when you do this, just drop it up underneath.
Sure, you just don't have the line to put it there.
And a closing curly brace. What have I done? I've blocked all of this in, so it's all being checked, just for convenience sake, right? And now by doing this, again, we can still catch the problem when it occurs right here. So let's demonstrate that real fast.
All right. Let's take checked away from this one line. So we'll take out checked, we'll take out the extra parentheses. Then we'll jump up right before we define our integers, say checked, drop down a line, open a block, drop down below the CC assignment right in here, finish that block, and I think that should do it.
And let's go ahead and put one of those to a 7, so like 127, just so that we're at our limits to show that it works fine. And wait, CC byte A++.
Okay, we need to drop the read lines in this because going back to our block scope, we wouldn't be able to see those.
Very good.
So we indeed can compile, we can run, and there's our 255.
So we're at our limit. Everything works fine, so let's go ahead and close. And then let's go ahead and set it to an 8 just to show that it does indeed catch the overflow. And caught the overflow. So overflow exception was unhandled. Beautiful. Okay, go ahead and stop execution. All right, and what hotkey are you hitting?
I'm hitting Shift F5.
Shift F5, guys, just in case you didn't know. Okay, so, and go ahead and set up the scope problem again. I think that's fantastic. It just drives home in the last video where we talked about this. Because right away, I didn't catch it in the first, you caught it before I did, so in the first 2 seconds, I looked at it, I was like, what the, and then you realize what it was. Yeah, there we go. Remember, block level scoping. So everything that is being defined or declared and initialized in here, we lose scope when we fall back out here, which makes CC no longer visible to us. So Logan needed to simply move this up into this area right here. So very important stuff. Keep that in mind.
It's very handy to be able to put checked around an entire block for convenience, so a lot of things could be checked. You also have to keep in mind that standard blocking scope still applies.
Absolutely. Now, you may be thinking, wow, I really don't want to have to go through all of my code and put checked in everywhere. That would be kind of a pain, wouldn't it, Logan?
Right. If for whatever reason the code you were writing would always break every time you had an overflow throughout your entire app.
Maybe or you just always want to check for an overflow. You're doing something that's critical with numbers or whatever.
That's true. It's very mission critical software.
Exactly. So how can we go about having this just be done automatically for us? It's quite simple. We can go ahead and set this by going to our solution properties. So if we right-click over here on Console Application 1.
So there's the solution.
And go down to our properties. And now from inside of, actually, no, hit cancel on that. Yeah, that guy.
That was project properties.
Yeah, project. I'm staring at solutions. Now go down to build.
All right, there's build.
And now scroll down to advanced.
Here we have.
And at the very bottom.
Advanced.
And then from in here, you're going to see the checkbox. The first checkbox that says check for arithmetic overflow or underflow. Just check that. And what that'll do is for this project here, all overflows will be checked. Okay, so it will throw an exception anytime that we have an overflow. Go ahead and hit cancel, though. We don't want to do that. But that might have you thinking, okay, well, if I do that, what if I have a particular area that I want to actually allow to overflow? Believe it or not, that is a technique that's used every now and then. Well, what if I want this to be able to wrap around? Well, instead of checked, we can use unchecked. So just put unchecked there, Logan, the UN in front of it. You'll notice that it still stays the keyword blue, just to indicate that's valid. I just wanted to point that out. So in this particular case, even if you go in and you set the project to always check by putting unchecked in there, everything's cool.
So you can have everything work the opposite. Like you said,
right.
Have everything be checked by default, but then still code in special cases where things are unchecked and an overflow could happen and not cause an exception.
You got it. So that will pretty much wrap up that quick discussion on overflows and explicit casting. But wait, there's more. That's right. Let's go ahead and bring this guy up and give ourselves another quick screen. All right, and on this screen, let us talk about another way we can explicitly convert. So explicit conversions using the convert command. Wow. You guys have already seen this. I think we've done toString a couple of times since the very beginning of this course, don't you?
Right. We have several times. I'm fuzzy on the exact specifics, but I'm
know
sure
we have. So, convert command. We've got a bunch of them that we can use. Let me just give you a very quick example. This is pretty simple stuff. If Logan comes in here and creates, let's say, a long, and calls it something like lvar, my Hungarian notation all of a sudden, equals 55, and then we have an int that is ivar. We can come in here and say system dot convert dot to int 32 and pass it lvar and terminate. And what this is going to do, the convert dot to int 32 is going to take this value. Basically, this guy right here, this method is overloaded several times. So it knows to take all of the different types in, basically. So it's going to take the type in, it'll realize what type it is, and then internally it knows how it needs to handle that type to explicitly convert it so that the result is then going to be an integer and fitting over here. So Logan, let's give this example to him real quick back over inside of Visual Studio.
Okay.
And then we're going to introduce a string with it, which is pretty nifty.
All right, I'm going to take out our checking example.
Okay.
And replace that with our example here, which begins with defining a long called lvar and initializing it to 55.
Okay.
Then defining an int called ivar and initializing it to system dot convert.
Yeah, we're just drawing out the whole thing so you can see it.
To int, there's int 32.
Look at all the twos. We'll talk about those in just a minute.
So to int 32, and what are we converting? We want to convert
lvar.
lvar.
And now we want to right line ivar.
So we'll jump down to our right line and replace that with ivar, and then that should be it.
And let's go ahead and run it. And look at that. 55 is now being stored in ivar, an integer data type. Okay, very nice. So let's go ahead and close out of that real quick and check this out. What I'm going to want to do is let's just have some fun. Watch this. I'm going to have you change two things, Logan. If I take long, don't worry about our naming convention. If I change that to a string, and I put quotes around this,
ooh,
that is definitely a string. Agreed?
Agreed.
Check this out. Try that and run it.
All right, let's take long, replace that with string. Well, string spelled like that. And then we'll place double quotes around 55 so that 55 is now a string.
It's definitely a string. We haven't changed anything else. Can we pull a rabbit from the hat? Let's run it. Look at that.
Indeed we can.
The number 55 is being stored in there. So that's what I'm talking about, how that method's overloaded like crazy. It knows all these different data types that you can send in there to it, and it's going to use the appropriate internal routine to convert that data type over to your required type. Now, we can also cause another exception error. We can cause a format exception error if you happen to throw an invalid format into a type. So it knows that this is a string, so it's expecting this to be a true string that can be converted over. Logan, right there, if you put in, I don't know, put a capital L in, or, yeah, there you go. Now, is this something that can be converted to a true number, 55L? No. Let's go ahead and run it, and we're going to see a format exception get called or thrown. Boom. Look at that. Format exception was unhandled. Once again, we can set ourselves up in a situation where we can catch these and deal with these problems if it is a possibility. Let's say we were using this with some sort of input screen where a user was allowed to type in a number, and we didn't have it locked to numbers. They could type in whatever because we were coding real quick, right? And they typed in, instead of, their birth date, suddenly just had letters in it for whatever reason. When we asked what month. I was born in 3X. Okay, that doesn't work. But we could catch that problem right here and handle it by telling the user, hey, excuse me, 3X doesn't work. Would you please enter something else? So I just wanted to demonstrate that to you. Very good stuff. So with that, let's just go ahead and stop execution. I'm going to jump back over here. Now, there are a whole lot of these different commands available. So basically, I'll just start right here. This is another area in the video. You can just fast forward real quick if you'd like. We've got convert. Of course, that's a capital C. Dot to Boolean. And it'll take in some sort of value that you pass it. And now I'm not going to write convert over and over and over because that'll just take forever. We can convert to byte. And all of these aren't, the reason I'm drawing out this table here, Logan, even though it doesn't look much like a table, is for the simple fact that right now it's like, well, yeah, these are obvious. They make sense. But int32, if you're not thinking about the data size, then what is an int32? Is it a long? Is it an integer? Well, we know that an int32 is going to be an integer. But right offhand, if I say an int64, what is it? You're on the spot and like, what is it? So
right, or if you just want to keep all the code more or less looking the same, if you've been working with chars or bytes or some other data type like long, it might actually make the code look nicer to say something like convert.toLong and convert.to.
Well, in this case, though, they're going to be.
Oh, I see. You're pointing out that.
I'm just pointing out what type. That's why I'm drawing this. I'm just drawing out.
I see. This is more like a reference table.
You got it. That's what I was trying to get at. Yeah. So we're going to convert dot to.
I see where we got the comments now for each of those. I was looking ahead in the chart.
Ah, I see. So what I'm going to start doing in just a second is this. This is converting to this. This, oh boy, this is a hard one. It's converting to this. This is converting to this. So far, so easy. This is converting to this. All right, so now we've got almost the interesting ones to double. Double's going to take in a val. And of course, it's converting over to a double. All right, so now let's start with some of our little ones. So we're going to start with a 2 int 16. I'm just going to pull in a val. This is converting to a short.
And this is where we get into the part where a lot of the integer data types were kind of unified in their naming as far as an actual .NET type, because technically short and int and long are all integers. They're all whole numbers.
Right.
The only thing that differs between them is the size.
Exactly.
And so that's what's reflected in these types here.
So 2 int 64 is going to be a long. So that's what I was getting at a second ago is, if somebody real quickly saw, N64, what type is it? What type,
Or just saw N32 and wondered where we had gotten into this world of other name types, type names.
So now we can come in here for some signed action. So we can say to signed byte. and send it a val. And of course, this can be a signed byte. To single. So here's another one that you may not have recognized right offhand. This is going to be a float. To string, one that we have used. Taking in a val and converting, of course, over to a string. Alright, let's see, we've got some more room, so let's just kind of scroll this on down like there. Alright, so the next one is going to be to an unsigned int 16. Takes in a val, and this will convert over to an unsigned short. Next one's going to be to an unsigned int 32, and a val, converting over to a simple unsigned int. And the final one is going to be to unsigned int 64. Converting over to an unsigned long. And my hand is falling off. There we go. So there are a bunch of different convert commands that you can use for converting data. Yay, I just wanted to show them to you. It's not over yet. We still have more we can show. Told you we're going to get something cool out of all of this. Alright, so next thing we want to do is just take a look at converting strings over to numeric data. But we're going to do this with another approach. We're going to use the parse functionality. This is cool stuff. So let's go ahead and jump in here and add yet one more page. And hide this one. Converting strings to numeric. Whoa, hey, that was a lot of fun, right?
There Photoshop goes with its jumping again.
Yeah, to numeric data. All right, so that is our goal here. That is an A, I do indeed promise. And we'll just draw a line back. There we go. Okay, so what I want to do, let me give you an example real quick. So we'll start out with string. And we'll give it a new name, my num. My num is going to be equal to, now I need to put an actual number inside this string here, so 135 is our daily winner. From there I'm going to come down here and create another variable. It'll be an integer value, an integer variable called inum. And it's going to be equal to, check this out, my type dot parse. And I'm going to feed it my num. So I am now taking my string, feeding it into here. Parse will take this information and convert it to an integer number. Logan, let's go ahead and code this in real quick just to demonstrate.
Okay. So once again, jumping back to Visual Studio, I'll take away the last example, and we'll jump in and define our string called mynum, and initialize it to the string 135 terminator. Then we'll declare an int. We'll set it. We'll name it inum, and we'll set it to int dot parse, and then we'll feed in the string mynum. All right.
Excellent. Okay, now let's go ahead and make sure we are writing out inum.
All right. So let me just put that in for our write line.
Okay, so everybody stare, absorb. All right, let's run it. We should see 135. And indeed, we see 135. Fantastic. But we can break this. So let's go ahead and close and watch Logan put a giant L in there, or Z, or whatever. Now Now it's no longer a true number inside there. I mean, it never was to begin with.
Or
it
even
was
better,
a string, but
let's do something like this, like 13Z5.
Yeah, it looks good
that
to me.
That would be hard for anyone to figure out without any instructions. What would you change it into number-wise?
Exactly. This is going to throw another format exception. Go ahead and run. And pow! And here we are. Format exception was unhandled. Yeah, that's not good. Okay. So let's go ahead and exit out of that. That means we would have to handle that, or we could use yet another approach, which is try parse. Now this is really cool stuff. This is all bonus stuff. I just want to throw this extra stuff in there. So we've seen this approach. So let me go ahead and just draw a line real quick. And allow me to rewrite this real quick. I'll make it fast. So string my num equals 1, 3, 5. And I'll have Logan change that, of course. And then what we're going to do is come down here and we're going to make another int, inum. But we're not going to initialize it. We're going to do something different. We're going to say if int dot try to parse. Now try to parse takes in 2 arguments. So we're going to send it my num. Why did I say inum? Hang on, let me back up. This is me getting carried away. No, I'm not. My num is the string. That's what I get for naming this in such a way that I can't quickly tell.
Phonetically, my num and inum. And
yeah, it's too close. All right, so we're going to send in the string, and then we need to tell it where we're going to put the result. We're using out. Now, please keep this in mind. Out has a very special meaning. We will be talking about this in detail later. Right now, here's what I want you to understand. Out is going to basically make sure that this inum right here is pulling information out of this method. It's going to be populated. The inum that resides back here will be populated with information that was come up with inside of try parse. So you can kind of think of it like the information's been thrown back out of there. Okay? Is that good enough, Logan?
Right.
I'm trying to keep this a very
simple. You're kind of saying that you want... Well, what it really boils down to is the fact that you have that in an if statement, which means that try parse is going to return a Boolean.
Yeah, which I'll talk about that part in a second.
But see, here's the tricky thing. You're trying to return a Boolean, but you're also trying to output a number, because that's what you're trying to do. You're trying to parse a number, so you have 2 things that need to go out. That's what that out was saying. That, all right, well, we need to put something else out. Let's put it into a variable.
Notice how Logan was talking fast? Let me tell you why Logan was talking fast. He was trying to go ahead and give you the out lecture right now. Out is something that you would use when you had a situation where you needed a method to return more than one thing.
Exactly.
Generally, you guys know that you've seen when you define a method, you could say that this method's going to return an int. Well, that's one type it's returning, or a string. But what happens if you need to return an int, a float, and a string? Well, now you have to use out to do it. But the bottom line is, what's going to happen is try parse will pull the number out of here if it can, and it will put it in inum. Now, the other key thing is, you notice this all resides, as Logan was just saying, inside an if statement, which means it is also going to kick back a true or a false. True meaning it was able to successfully populate inum with a true number. False if it could not. So I could simply come in here and say, I'll have you write something, Logan, but I'll just say worked, else. So this is where you don't have to go in there and set up all this exception handling and all of this stuff. You've got it right here. Did not work. Okay, so once again, it's int.try parse, and it's looking for you to send it the string first, so the string variable, and then it's going to look for out and the variable that you're going to send it to. So I'll just say int, that'll work. And that is what you need to know. But Logan, let's go ahead and jump back over into Visual Studio and code this now so that they can see it.
All right, we've got, again, a string
He didn't have to delete that, did he, guys?
I guess not.
No, that was funny. All right, so my num equals 135. Okay, and now int inum.
So inum, not going to initialize it yet.
Right, now we're going to jump down to an if.
All right, so if int,
because that's what we need to cast it to.
Try parse, and then we'll feed in the string that we want to try to parse, which is my num.
And check it out. Look at what Logan's got right there with the overloading. It knows. So first it's looking for the string, so that's going to be my num, and then go ahead and do a comma. And now it tells you. Now it needs an out, and then an integer result, since it's int that we're using, int.tryParse. So the integer result in this case will be inum.
So this will be out inum.
Beautiful. And close, and close. One more parentheses.
Oh, yeah. It was Terminator? No. New line? No.
There we go.
Okay, there we go.
Okay, so now you can drop down and you can do console write line, and you can just write the value out.
So console, we'll have that write out inum.
Otherwise, have it write out invalid. Or you could say, start out with, in the write line, do my num plus.
So my.
No. Actually, you do. We're going to put the value of
the string. So
yeah,
my
string.
num
Plus space, yeah, and then is not a valid number.
Is not a valid number.
Beautiful. All right, so let's go ahead and run this, and we should see 135.
So
well, yeah, we can go ahead and comment out that.
We don't need that one
Yeah,
anymore.
just delete it. All right, let's go ahead and run. And 135, because it is indeed a valid number. Now throw a couple Z's in there or something.
All right, a few Z's for good measure.
Run it again.
Let's run.
Check it out. This time we did not throw a format exception error. Instead, look what we got. 135ZZ is not a valid number. That's handy. That is very handy.
So you have a lot of fun with that.
Cat is not a valid number. This is true. Now I'll put 322. And 322 is a valid number. Woohoo. Okay, so, wow. 322 cats. Oh, that's a scary person to have 322 cats. Okay, guys. I think, Logan, this is probably where we need to bring it to a close. I mean, we can obviously talk about the conversion of one data type to another all day long, but because there's still a lot further that we can go. I mean, we still have, well, other things. I don't want to really take it outside of the scope that we've got defined at the moment. But I think we've covered quite a few things. I mean, we've talked about implicit casting. We've talked about explicit casting. We've talked about using the convert to method or the convert method. And then from there, we've taken a look at parse and try parse. So we've shown quite a few things.
Stuff like overflow and
yeah, we've looked at overflows.
Problems that can cause and ways to prevent or check the problems.
You got it. So is there anything else you'd like to add?
No, I think that covers it.
Okay, fantastic. Well, with that, that is going to wrap up this video on casting. Thanks a lot.